Okay, this is the second part of our organic chemistry video, and I want to remind you that this is never tested. Never. The whole purpose of this is to get you literate in organic chemistry so that when you see the names, you have a rough idea of what's going on. Okay, so last time we only looked at alkanes, which were single bonds only, carbons and H's. What if there was a double bond? So here we have a propane because it's got 3 carbons, and you'll notice that I'm getting a little bit lazy. I'm not writing the H's anymore. This is a butane. It's got 4 carbons, but this one has a double bond in it. 4 carbons with a double bond is called butene. And this one's 4 carbons with a double bond in it. So that one's butene all. Oh, that can't be. So what we have is an issue with addresses again. So whenever we name these things, we're not going to be as simple as this. We're going to say that the double bond occurs in the first position here. So we're going to call that 1-butene so that you tell the reader where the double bond is. And then this one would be the second bond, so it would be 2-butene because it's the second bond over. Now, one thing you may notice is that alkanes, carbons and hydrogens only, all single bonds, they have a relationship between their carbons and their hydrogens. So if we did 3 carbons like we did up here, 1, 2, 3, we could put in 1, 2, 3, 4, 5, 6, 7, 8 hydrogens. So that would be 8 hydrogens. Or if I multiplied by 2, so 3 times 2, and added 2, I can get my carbons and hydrogens. This carbon needs 4 bonds. So if we did 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 4 carbons has 10 hydrogens. Or 4 times 2 is 8 plus 2 is 10. If you do the same thing for alkenes, carbons and hydrogens only, but there's a double bond in there, then they have a different relationship between their carbons and their hydrogens. If you double the number of carbons, you get your number of hydrogens. Okay, there's also something else that's weird about double bonds. They don't rotate like single bonds do. In the last video, I said, hey, it doesn't matter whether a carbon chain like suddenly bends and goes in a different direction. Because with single bonds, bends like this are not important. But with a double bond, bends are actually really important. And to stress that, they get a prefix, either a trans or a cis prefix added to their name. And the way you figure it out is I draw a dotted line that goes through the double bond. Okay. And if the main chain crosses across that double bond, excuse me, then it is trans. And if the main chain never actually crosses the line, that dotted line, it's called cis. So you can touch the line, but if you don't cross it, you are cis. And if you cross the line, you are trans. Now, trans literally means across, and cis literally means like to stay on the same side. Okay, so again, you don't need to know this, but if you ever saw a like trans 2-butene, you would know that it was 4 carbons, that there was a double bond, that the double bond occurred in the second position, and that it went across the imaginary dotted line. So it would be this molecule here, which would be trans 2-butene. This one would be called cis 2-butene. What if there's a triple bond? Those are called alkynes with a YNE ending. And you can see like this is butane and this is wait a minute, we have the same issue. So we need, again, to identify where the triple bond is going to be. So this is just going to be 1 butane. This is going to be 2 butane. And if you're looking ahead, this is going to be 3. No, it is not going to be 3 butane. Remember, you always want to give the lowest possible address, because this molecule, if I picked it up and flipped it over, this bond would appear over here. So these two molecules are the same molecule. It's just 1 butane. They also have a relationship between their carbons and their hydrogens. If you had 4 carbons, you would say 4 times 2 is 8, minus 2 is 6. You would have 6 hydrogens. So if we put those in place, this carbon already has 3 bonds, so it could take 1 hydrogen. Oh, sorry. This one has 4 bonds, 1, 2, 3, 4. So no hydrogens here. This one has 2, so we could put 2 hydrogens on it. And this one has 1 bond, so we could put 3. Or 1, 2, 3, 4, 5, 6, 7. So how's that work? Oh, what am I doing? That wasn't an H there, and I get my 6. Sorry about that. What if we put our carbons in a loop? So a carbon chain that just doubles back on itself. When this happens, it's all carbons and hydrogens, which I'm too lazy to draw. And so this is a 1, 2, 3, 4, 5, 6 carbon loop. So we would call it cyclohexane. And the cyclo part just tells you that you are going in a cycle or a loop. The hex tells you that it's 6 carbons, and the ane tells you that it has all single bonds. This has 5 carbons, so it would be cyclopentane. And this one, we've got 3 double bonds in this cyclohexane here. So it's no longer a hexane, it would be cyclohexene. And we would put the double bonds in the first position, the third, and the fifth. So you could call it 1, 3, 5, cyclo hexatriene, because there are 3 double bonds. Now, that's too miserable. So see how these names keep getting longer and longer? So chemists start to do weird things. They actually just called this thing a benzene. So that one's important because you see it a lot. It's a chemical that occurs a lot, especially on the tests. So if we get lazier, what we can do is write this thing as sticks. Each time the sticks bend is going to be a carbon. So this is really a carbon, 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 with double bonds occurring between the first, third, and fifth. Or because this happens so often in chemistry, instead of writing the individual bonds, because who's to say they occur here, here, and here, why couldn't they occur here, here, and here, which we'll talk about later. And we will call this thing like an aromatic, and we'll get super lazy and just draw a circle that says there are double bonds in here and they're all over the place. How lazy can you get? So to correctly write out a pentane, you should write out your 5 carbons with all their hydrogens attached, but that's a lot of work. So what you'll see is that sometimes chemists just write out the carbon chain because a good chemist is going to know where the hydrogens are based on the chain. But you can get lazier than that. You can use the sticks that I just introduced, and anytime a stick bends, that is a carbon. So we have 1, 2, 3, 4, 5 carbons. And like any good carbon chain, there's going to be hydrogens here that are attached that the chemist would just assume you would know how to attach because you know what you're doing. So what is this thing? Well, it's a carbon, and a carbon. So that's a propane, but it's got a double bond. So it's a propene. And you might think that it is one propene, but the one is not written. What if I put the double bond here instead? That would still be one propene because you're always going to name it as the lowest possible number. So it just gets the number propene. It actually doesn't need a number because there's only one possible number. And then this thing, it's a 5-sided cycle. So it's going to be a cyclopropene because of the double bond. And we would say it was one cyclopropene because it just has one bond, or probably more likely just cyclopropene, because if there's only one of them, it has to be in the first position. So you will see chemists just start to write sticks and assume that anytime those sticks bend or branch off, there is another carbon there. Okay, to end this thing, there's one more piece left, and these things are called functional groups. And there's a lot of them. I don't want you to memorize these. They're pretty much useless, except that they make the organic names get crazier and crazier. As we've already pointed out, there's anes, enes, and ines. I said earlier that there's aromatics that are rings that have multiple double bonds. If you put a halogen on something, it's called a halide. Alcohols always have an OH group that's attached to them. So you'll see that a lot, and we will actually talk about that more when we talk about our acid and base unit. But the things that I need you to hold on to, because they will be important on the tests, are that COOH thing. So if you look through all of these things, looking for COOHs, here's a COOP. Nope, that's no good. Another COOC, that's no good. But here is a COOH. And like I told you, it is an acid. So I need you to hold on to that. The other thing I told you to be wary about is anytime you see a weird N here, weird N here. I'm sure there's another one somewhere. Over here is another weird N. Those are all bases. So actually, let me go back. Base, base, base. So these guys are bases. And this thing is obviously an acid. So anytime you see a functional group, it will have a weird ending to its name. It might end in an ONE, or it might call itself an ester or an amine. But your job is not to freak out and just to know, oh, it's going to be a crazy organic molecule, and to keep your eyes open for that COOH or that weird N.